Human rights matter, but conversations about rights can be polarizing, confusing, and frustrating. Lawyers Claudia Flores and Tom Ginsberg have traveled the world getting into the weeds of global human rights debates. On Untitled, a new podcast from the University of Chicago Podcast Network, they use that expertise to explore the stories and thorny questions around why rights matter and what's the matter with rights. Subscribe to Untitled, part of the award-winning University of Chicago Podcast Network. If you're a regular listener of our show, you're probably used to us talking about how there are things about our universe that our standard model of particle physics doesn't have answers to, no matter how successful it is on its own. And in our last episode, we hit on one of them.
So last time in Why This Universe, we talked about how neutrinos, these particles called neutrinos, can transform from one kind of neutrino into another. For example, an electron neutrino can travel through space and then kind of spontaneously become a muon neutrino, or a tau neutrino. We call these transitions neutrino oscillations. And it turns out that for a neutrino to oscillate into another kind of neutrino, these particles have to have mass, and furthermore, the different neutrinos have to have different amounts of mass. Based on the measurements we've made of oscillating neutrinos, we've deduced that the sum of the three neutrino masses has to be at least 0.06 electron volts. So if you add up all three of the masses, they have to be at least this number. And that's about 10 million times smaller than the mass of an electron. So this is a really tiny mass, but it's not zero.
The fact that neutrinos aren't massless was a big surprise to physicists, because it's in conflict with what we expect from our standard model of particle physics. Up until this point, physicists thought that they had a pretty good understanding of how particles get their masses, and it all has to do with something called the Higgs field.
The Higgs field can interact with particles in a way that causes them to act like they have mass. We sometimes say that the Higgs field gives a particle its mass, and that's what we mean. They interact in a way that causes these particles to behave like they have mass. We call this the Higgs mechanism, and as far as we can tell, pretty much all of the known particles get their mass in this way. The electrons, muons, quarks, W and Z bosons, all of these particles get their mass through the Higgs mechanism by interacting with the Higgs field that goes out throughout all space.
So to understand why neutrinos don't fit into this picture, we have to talk about a weird feature of particles that sometimes is swept under the rug. This feature is called spin. As a physics undergrad, spin was always super confusing to me because it doesn't mean that the particles are literally spinning, like the Earth rotating about its axis or anything like that. But what it does mean is that some particles act as if they have an intrinsic kind of spinning, or an intrinsic angular momentum. Unlike a spinning planet, though, the spin of each particle doesn't change based on how the particle is moving. It's like a set property of each kind of particle. And it can only go in one of two directions, like clockwise and counterclockwise, for example. We can think of a particle spinning in one direction as being left-handed, and a particle spinning in the opposite direction as being right-handed. And it turns out that this handedness comes into play in the way that particles interact with that Higgs field we were talking about.
In the case of the quarks and the particles we call charged leptons, so these are electron, muon, and tau, the Higgs gives these particles their mass by interacting both with particles that are spinning clockwise and counterclockwise. So we call this left and right-handed particles. And you need both. If you only have one or the other, this mechanism won't work. So this works fine for electrons and quarks and things like this, but it doesn't work for neutrinos. Neutrinos are different from these other particles because they only spin counterclockwise. They're always left-handed. Without the existence of any right-handed neutrinos, the Higgs mechanism shouldn't work on them at all. And that means the neutrinos should be exactly massless, which of course they aren't. So this empirical fact that neutrinos oscillate and therefore have mass tells us that our picture can't be complete here. There must be some way that these particles get mass. And our best guess as to how this happens is that, in fact, those right-handed neutrinos that don't exist in the standard model, they must be out there. there must be something that allows those left-handed neutrinos to interact with the Higgs field in a way that gives mass, even though we've never seen these particles and they're not part of the standard model.
So in the rest of today's episode, we explore whether these elusive right-handed neutrinos exist, and if they do, what could they tell us about the world beyond our standard model of particle physics? You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago.
So we've talked about how neutrino oscillations lead us to believe that a new kind of particle might exist, a type of neutrino that's right-handed or spinning in the opposite way of all the neutrinos that we do observe. But this particle doesn't fit into our standard model of particle physics.
Despite the considerable successes of the standard model, this shouldn't surprise us too much that it's incomplete. Standard model doesn't have any explanation for dark matter. It doesn't have any explanation for the hierarchy problem or quantum gravity or so on and so forth. So we know there's got to be more to, the laws of physics of the universe than the standard model has, and maybe right-handed neutrinos are just like a part of that. But even if these right-handed neutrinos do exist, they can't just be the right-handed copies of the ordinary neutrinos. Whatever these things are, they don't interact the way that left-handed or ordinary neutrinos do. In particular, whereas the left-handed neutrino experiences the weak nuclear force, the right-handed neutrinos just can't. They don't fit into the theory that way. So whereas the ordinary neutrinos are very ghostly and interact very, very rarely, it's even triply true for right-handed neutrinos. They essentially never interact with anything to a pretty high degree of approximation. They're ghosts of ghosts of ghosts, making them almost impossible to detect in any plausible experiment.
Right, which would also explain why we haven't seen them yet.
Absolutely. If a universe could be full of right-handed neutrinos, and it would be very hard to tell. So the ordinary neutrinos in the standard model are sometimes called active neutrinos. And all we mean by that is that they experience the weak force in an active way. They can scatter off things. They can, be produced and otherwise interact through the weak nuclear force. But these right-handed neutrinos don't experience that force, so we don't think of them as active neutrinos. Instead, we call them sterile neutrinos, basically unable to interact except through the force of gravity with the kinds of matter and energy that otherwise exist in our universe. The sterile and active neutrinos, in addition to having these different kinds of interactions, could be different in other ways as well. For one thing, there's no reason to think that the sterile neutrinos have to have the same amount of mass as their left-handed active neutrino counterparts. They could have similar masses, that's a logical possibility, but the right-handed neutrinos could also be much, much heavier. They could be, thousands or millions or billions or trillions of times as heavy. In some grand unified theories, for example, the right-handed neutrinos are predicted to be extremely heavy, trillions of times heavier than even the heaviest known particles.
Wow. So they're just kind of like boulders like floating around the universe that we just can't see.
Yeah. Even the heaviest particles aren't heavy by, boulder standards, but they could be
metaphorically.
Yeah. But a trillion Higgs bosons all glued together, would still be a pretty small object by, macroscopic scales.
Okay, so maybe they aren't literally the size of boulders, but these heavy sterile neutrinos are quite the object of interest for another metaphorically big reason.
In my research, there are a few questions I think about more often than that of dark matter. And as someone who thinks a lot about dark matter, sterile neutrinos have some features that are really grab my attention. I mean, just think about it. So sterile neutrinos are heavy particles. They're super feebly interacting. They could be very long-lived. They could live longer than the age of the universe. These are all the things that make something an ideal candidate for dark matter. So if somehow enough sterile neutrinos were created and the universe was young and hot, then maybe the dark matter could all be made up of these sterile neutrinos, these right-handed neutrinos.
For physicists, this is like theoretical gold. A particle designed to solve one problem, neutrino masses, ends up being a candidate to solve a whole other open problem, what the dark matter is. Possibilities like this are very, very compelling.
The trick, it turns out, is in figuring out how these particles would have been created. Traditional WIMPs, or weakly interacting massive particles, are our kind of default idea for what dark matter is. These things are produced in huge numbers in the early universe, and like a small fraction survive, and they go on to be the dark matter. But in the kind of sterile neutrino models that most often been written down, nothing like this takes place. There were never very many sterile neutrinos in the early universe. They just don't interact enough to be created in that way. So if we wanted to explain dark matter in terms of sterile neutrinos, we need some new way of creating these particles in the early universe. So back in 1993, my friend and former Fermilab colleague Scott Dodelson and his collaborator Larry Woodrow wrote a paper that proposed a way that the early universe could create a large abundance of sterile neutrinos. What they suggested was that when the universe was young and hot, these sterile neutrinos could have been produced through the oscillations of active neutrinos. So just like active neutrinos can change from one flavor to another, they proposed that these active neutrinos could change from active to sterile neutrinos, basically turning into dark matter. So over time, you could imagine that in the first second or so after the Big Bang, you could build up an abundance of these sterile neutrinos, and you could be left with enough to make up the dark matter of our universe. It's really a pretty elegant picture, and it held together pretty well. Now, bear in mind that at the time, there's still no conclusive evidence that neutrinos had mass or oscillated or anything, so it was a really kind of bold thing to be suggesting as early as 1993. But a few years later, when neutrinos were observed to be oscillating, it gave people good reason to think that this could be part of reality.
So this is suggesting that sterile neutrinos can oscillate back and forth into normal neutrinos. But we know that the dark matter has to be stable. So is the idea that oscillating happens at a consistent rate and so it is stable? Or is it, you produce enough sterile neutrinos and then eventually they oscillate less?
So the kind of oscillations that Dodelson and Woodrow were talking about are a little bit different from the kind that we normally think about with active neutrinos. So let's say an active neutrino gets made in the sun and starts traveling towards the Earth. It might start out as an electron neutrino, and then by the time it reaches us, it's mostly muon or tau neutrino or something. That all happens in vacuum. But what can happen in the early universe is an active neutrino can collide with something because it's hot and dense, and these collisions are happening all the time. And instead of coming out as an active neutrino, it can oscillate into the heavier right-handed neutrino. And then once it's in that state, it won't meaningfully oscillate in a way that takes away the dark matter. It will basically stay in that state throughout cosmic history. So in the picture that was put forth by Dodelson and Woodrow, the sterile neutrinos that make up the dark matter would have to be heavier than about 1 kiloelectron volt or so, or about a 500th of the electron's mass. This is a pretty light number, mass, but it's a lot heavier than the active neutrinos, which are, very, very, very light. It turns out there are at least two good reasons why these sterile neutrinos, if they make up the dark matter, couldn't be lighter than that. One has to do with something called the Pauli exclusion principle, which you might have heard about in a chemistry class you might have taken at some point. This rule basically says that any given particle, like an electron or whatever, can only be in a specific state if there's no other particle like it that's already occupying that state. And it turns out that this law doesn't only apply to electrons, but all the particles called fermions, including neutrinos. It follows directly from the Schrödinger equation in quantum mechanics. So if you apply the Pauli exclusion principle to the case of neutrinos, you can deduce that no two neutrinos can be in exactly the same state at the same time. And this fundamentally limits how many neutrinos of a given velocity you can kind of cram into one piece of space. So if the sterile neutrinos were lighter than about 1 kiloelectron volt or so, you just couldn't fit enough of them into the smallest galaxies. So the fact that these small galaxies exist with the densities they have tell us that if the dark matter is a sterile neutrino or really any other kind of fermion, they have to be heavier than about a keV, a kiloelectron volt. Secondly, if the sterile neutrinos were much lighter than this, then they would be an example of what cosmologists call hot dark matter.
By hot, we mean that they would be moving very fast, at speeds near the speed of light, where Einstein's theory of special relativity becomes very, very relevant.
So whereas cold dark matter particles were traveling very slowly when galaxies started to be formed, in a relatively early universe, hot dark matter were still moving really quickly at that time, and their motion would have prevented the smallest galaxies from ever forming. From the fact that these small galaxies exist in our universe, we can deduce that the dark matter can't consist of sterile neutrinos that are lighter than a few or several kiloelectron volts. That kind of gives us a lower limit on how massive these particles could be. Okay, so we've got ourselves a pretty good dark matter candidate in the form of sterile neutrinos that were created in the early universe through oscillations. The question then is, how do we test that hypothesis? Well, it turns out that while these sterile neutrinos are pretty stable, they're not perfectly stable. They eventually decay. For example, if the sterile neutrinos were about 10 kiloelectron volts in mass, they would have a lifetime or a half-life of about 10 to the 15 years. So 1,000 trillion years, which is about 100,000 times longer than the age of the universe. So far in the course of the entire universe's history, 1 part in 100,000 of the dark matter would have decayed, and the rest of it would still be there. And that's fine. We don't have a measurement of the total dark matter abundance at 1 part in 100,000, so we would never notice that. But what we might notice are the particles that are created in these decays. So in most of these sterile neutrino decays, the sterile neutrino disappears and is replaced by 3 ordinary active neutrinos, which are really hard to detect, and probably we would never be able to see those. So that's not a problem. But in a small fraction of the decays, about 0.4% of all the decays, the sterile neutrinos instead transform into 1 ordinary neutrino and a photon. Photons in general are not that hard to detect, so maybe we could use this as a way to see if we can test the sterile neutrino dark matter hypothesis. Making it even better is the fact that in these decays, every single one of these photons that are produced will have the same amount of energy, equal to half of the mass of the sterile neutrino. So, for example, if the sterile neutrinos were 10 kiloelectron volts in mass, all these photons will have an energy of 5 kiloelectron volts, giving us a distinctive spectral feature that we can look for with our telescopes. So at 5 keV, kiloelectron volts, we're talking about X-rays. That's what these photons will be. And we have really powerful X-ray telescopes that we can look for this sort of feature with. So over the last, few decades, we've been looking for this sort of feature with X-ray telescopes, and we haven't really seen anything. And more or less, the lack of that signal has allowed us to pretty much rule out the Dodelson-Woodrow model. That first sterile neutrino model that was proposed back in 1993, well, if it were real and all the dark matter consisted of those sorts of particles, we really should have seen this X-ray line by now, and it's just not there. You might think that once a theory like this has been tested, it would just go away. Like, we just wouldn't be doing this podcast on sterile neutrinos as dark matter right now.
Yeah, you're probably did I just waste my last 20 minutes?
Well, you might have, but not for that reason. In practice, physicists often find ways to take a theory that was once viable, but it then was ruled out, and change it or tweak it or modify it in some way to evade those constraints, to make it a viable theory again. This kind of makes some of these theories like a moving target. And some people criticize this sort of thing, but as I see it as a healthy part of the scientific method, it's just how science and scientists respond to new data. The key point is that we change our views about the universe when new data come in. And in this case, that change might be replacing the original idea of Dodelson-Woodrow with a new idea. In this case, the new idea came in 1999 by Shangdong Shi and George Fuller. And in their original paper, she and Fuller pointed out that you might be able to make even more sterile neutrinos in the early universe if there's way more leptons than anti-leptons in the early universe. So let me unpack that. So leptons are things like neutrinos and electrons, muons, and taus. And they all have antimatter counterparts, anti-electrons, positrons, anti-muons, and anti-taus. And we generally guess that they were abundant in the same quantities in the early universe. But if there were way more leptons than anti-leptons, you can make more of these sterile neutrinos without making as bright a line of the X-ray line that we're looking for. So you can hide these sorts of neutrinos better from X-ray telescopes while still doing all the things that you want your sterile neutrino dark matter to do.
There already was a good reason to think that there's more matter than antimatter in our universe. Every time matter comes in contact with antimatter, they annihilate. But the world around us is mostly matter. Our planets, our stars, us. And all of this matter must have been left over after all of those annihilations with antimatter. So, in the early universe, there must have been a tiny bit more matter than antimatter. Like for every 10 billion antimatter particles, there'd be 10 billion and 1 matter particles, so that after the annihilations, matter remained. We talked about this more in depth in episode 4, if you want to hear more, but the thing is, in this case, with leptons and antileptons, the difference is much, much bigger. There have to be way more electrons than anti-electrons in the universe, for example, for this to work.
So, looking to the future, I think we should be able to pretty definitively test this hypothesis that sterile neutrinos can make up all the dark matter, at least for the kinds of sterile neutrinos that we're talking about in this episode of Why This Universe. Roughly speaking, to hold this whole picture together, the sterile neutrinos have to be in the range of several keV, or kiloelectron volts of mass, up to about 100 kiloelectron volts of mass. In the highest part of that range, you should be able to test this with X-ray telescopes. Maybe not quite yet, but in the pretty near future, you should be able to see with enough sensitivity the X-ray sky to test whether these things are really there. And then on the low mass part of this range, these sterile neutrinos, because they would be hot or warm enough to influence the smallest galaxies that we see in our universe. And as our galaxy surveys and telescopes discover more and more of these small dwarf galaxies, the more we can kind of push up the minimum mass of these sterile neutrinos. And eventually, I think in the coming years, we'll be able to either, determine that sterile neutrinos really do make up the dark matter, or rule out this class of pictures.
But even if sterile neutrinos don't make up the dark matter, they might still be out there, helping us answer the question we started with about how neutrinos have mass, and still bringing us closer to understanding these questions that exist at the frontier of physics. Thank you so much for listening to Why This Universe. If you want to support us more and get access to some exclusive content like exclusive interview clips, Ask Me Anything episodes, the opportunity to ask us questions, and a free sticker, you should definitely join us on Patreon. You can find us at patreon.com/whythisuniverse, and we really appreciate all the support that we get through there. Today's episode was produced and edited by me, Shalma Wegsman. My co-host is Dan Hooper, a professor of physics at the University of Chicago and Fermilab. He's also the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jake Kleinbaum. And Why This Universe is brought to you by the University of Chicago Podcast Network.